We are now looking at the domain of continuous relations. Remember that a discrete relation consisted of a list of unconnected ordered pairs. We could list out the specific ordered pairs in a discrete relation. For the graphs on this page, that is not possible. These are all continuous relations. The ordered pairs on each of these graphs are connected, meaning that each of these relations consists of an infinite number of ordered pairs. We can't just list them out. If you picked any of these graphs and started to write down every single ordered pair that is graphed, you would be doing so for the rest of your life. Really. What this means is that when we're writing down the domain of a continuous relation, we can't do it in the same way that we could for a discrete relation. Recall when we were writing down the domain of a discrete relation, we could just write, using set notation, a list of the x values. These are the specific x values in this relation. There aren't any more, only x equals -3, 0, 5, 8, and 10. For this relation, the only possible x values are -10, 4, and 25. Here, the only points on this graph have x values of -6, -4, 1, 2, and 5. That's it. That's the whole domain. You cannot write a list like that for a continuous relation. A continuous relation, again, is connected. If we tried to do that, and you may think you can do that, let's look at this first example. So we could see there's a point on the graph for x equals 0. There's a point on the graph for x equals 1. This point has an x-coordinate of 2. This point has an x-coordinate of 3. This point on the graph has an x-coordinate of 4. And so you might think you could just write curly brackets 0, 1, 2, 3, 4. That is the domain of this relation. Well, that's part of the domain, but that's not the entire domain. Because those ordered pairs, this one and this one and this one and this one are all connected, every single x value in between these integer values also is in the domain. So there's a point on the graph where x is a half, and where x is 2/3, and where x is 1.1, and where x is 2.6. And because of this arrow, there's actually a point on this graph for every x value bigger than that, where x is 10, and 100, and 1,000, and 1,000,000. That means for a continuous relation, we're going to represent our domain using an inequality statement. What inequality are we going to use to say that x can be 0, or 1, or 2, or 3, or 5, or a billion, and every decimal value in between? What we're going to write is x is greater than or equal to 0. There is a point on this graph that has an x-coordinate of 0, and there is a point on this graph for every x value bigger than 0. This is the type of inequality statement we will be writing whenever there's a minimum value of x. Please notice this arrow is really important, and that's what tells us that x goes on and on and on forever. It can be anything bigger than 0. This arrow indicates that this ray goes down forever and to the right forever. For the domain, what's important is that the graph goes forever to the right. So forever in this direction, in the right direction, toward positive infinity for x. This next graph looks really different, but our domain statement is going to be similar. When we're figuring out the domain, basically what we're doing is taking this two-dimensional graph and squishing it onto a one-dimensional number line, thinking what part of our number line, our x-axis, is taken up. So there's no point on this graph where x is negative, 1, 2, 3, 4, 5. There's no point on this graph with an x value of -5, or -4, or -3. There is a point on the graph where x is -2, and -1, and 1. For each of these, there's 2 points on the graph. Doesn't matter that there's 2 points for the domain, but it's the case. There's a point on the graph, actually 2 points, where x is 1, and 2, and 3, and 4, and again, because of these arrows, for 10, and 20, and 30, and 1,000. Just like our first graph, there is an ordered pair on this graph for every point in between as well. What that means is the The domain of this graph can be represented by the inequality of this squished up one-dimensional number line representation. So x can be -2 or -1 or 0 or 1 or 2 or 3 or 4 and every decimal in between. What inequality are we going to write for that? We're going to write x is greater than or equal to -2. If we look at the points on the graph, there's a point where x is -2, -1, 0, 1, 2, 3, 4, and so on. Similarly, we will write an inequality statement if there is a maximum rather than a minimum, as was the case here. So there was a left bound or a minimum. If there's a right bound or a maximum, a similar inequality will be written. So for this graph, there is no x-coordinate, no point on the graph with an x-coordinate of 3. But there is one for x equals 2 and 1 and 0 and -1 and -2 and -3 and so on. Because of this arrow, the graph goes forever now to the left, to -infinity. That means x can't be 3, but it can be anything less than 3. There is a point on this graph with an x-coordinate of any value less than 3. Because of this open dot, we don't have an equal to symbol. So if there's no dot at all, there's a closed dot, no dot at all, we assume it's a closed dot. We will show you it's an open dot to say, hey, this point is not on the graph, x cannot be 3. Second example of a maximum or a right bound. For this graph, x can be 3. Wow, do these have the same domain? That's pretty cool. Almost. X can be 3, x can be 2, x can be 1, x can be 0, x can be -3, -5, -50, -10,000. X can be 3 in this case, and it can be anything less than 3. When I say x can be 3, I mean there's a point on this graph for each of those x coordinates. And in fact, there's 2 points for most. That means I'm going to write x is less than or equal to 3.